Hello, this is Dr. Muhammad, and this is another video under design of steel structures according to AISC. Still we are under beam column, and the contents for today I'm going to explain about B2, the amplification factor for the moments occurring when frame is not braced against side sway, the case of unbraced or not braced condition, and then I'm going to give an example after that. If you didn't watch the previous video, please revisit or visit the previous video and watch it, because it has an important principles that is going to help us understanding the contribution of the amplification factor B2. So if you didn't watch it, please watch it first and then watch this video. As we said in the previous video, B2, it is amplification factor. What is the meaning of amplification factor? Means that we're going to multiply the original moment, which is here in this case M lateral translation, okay, with a magnification factor. We call this B2, in order to take into consideration what we have mentioned about it last time, which is the big delta, P delta effect, right? If we say that the two ends of the member is going to be not going to move to one another, then we are going to use B1. But if there is lateral movement, then we are going to use B2, and in this case we are going to take into consideration the second or the secondary moment called P delta or large delta effect. Okay, so this amplification factor for moments occurring when frame is not braced against side sway. Frame is not braced against side sway. Okay, so this is the case for B2, and B2, it is the amplification factor to incorporate P delta effect, the large P delta effect, as I said. Okay. Now let's go directly and see how we can calculate B2. If you remember from the previous video, we said that B1, it was having something called Cm here, right? And then we are having like alpha 1 minus here and alpha times PR over PE1. Do you remember this equation? And we have explained the story of Cm and how it takes into consideration the moment distribution, and we mentioned about PE1 and PR, how to calculate every parameter here. But whenever that you look to the B2, which is the amplification factor for moment in case of side sway, you are not going to find Cm here. It is only one here. Okay, this is an important difference between B1 and B2. And in the same time, you are going to see that in the denominator we are going to have alpha as it was here, but the summation of no translational moment is going to be used here. Okay, sigma P and T, it is the sum of the required load capacities of all columns. Okay, what we call it, the summation of P and T, it is the sum of required load capacities for all columns in the story under consideration. Okay, this is of course factored for LRFD and unfactored for ASD. And the summation of PE2, it is the sum of Euler loads. So here this is related to the required loads. Here it is related to Euler loads for all columns. So we are having a ratio between required load capacities. This is the required, which is like the applied load in case of ASD, or the factored load in case of LRFD, and the Euler load, which is seemingly to be like the capacities, buckling capacities of the columns. For all columns, we are talking about all columns. As you can see here, there is significant difference also, the word all. Before in B1 we were talking about individual column, because we are talking about the individual element itself, delta. Here we're not talking about this. We are talking about the entire story means that if the story is having many columns, then we are talking about the entire story, because the entire story is going to move with the same delta. So we're going to find a keyword that is being repeated in the definition of summation of PNT and in the definition of summation of PE2, which is the all, word all columns in the story. So we're talking about story here. You can consider B2 is viewed as global amplification factor for all columns. However, B1, it is local amplification factor. Okay, and then as we said, this is the same as we have used them in B1 and B2. But BR here it is BNT, and BE1 it is BE2 here. Okay, this is BE2 means that it is Euler load for all columns in the story. Okay. Okay. In our case here, whenever that we are looking to how this P delta effect is going to be taken into consideration, we have here, this is the column, let's assume AB for example. One end, which is end A, is going to move laterally with delta, and the axial force and the moment that is being applied on the element, which is P and M node, is going to be applied, and we are going to find that this can be decomposed of two parts together, which is we're going to provide two different moments. The first one is M node, which is with the same magnitude, but as you can see here, they are in different signs, with different signs, for example. And here this is related to the secondary moment. So this is the primary moment, and this is the secondary moment, which is P delta. The effect of the two is going to be superimposed, or the effect is additive. This means that we are going to superimpose the moment coming from the primary moment and moment coming from the secondary moment, or P delta effect, and then we're going to obtain something like this. This is the shape of the final moment that we are expecting M maximum here. Okay, this is when we have in a frame that is not braced against sidesway, we do not see any kind of bracings here, and it is exposed to gravity loading as well as lateral loading. Okay, so we have gravity here, and we have gravity, and we have lateral as well. Okay. Okay. There are two forms of the Euler load given. Okay, when we are going to calculate Euler load in the denominator, we have two forms. One form is related to the summation here of pi squared EI over K2L to the power 2, which is the most common and traditional equation of Euler load, but the summation is here. Okay, you can find this in AISC equation C2-6a, and here we are going to find another form of the equation, which is related to the summation of HL over delta H. What is HL? Summation of H, it is the horizontal load that is being applied on the system, and L, it is the story height. And this deflection, which is going to be delta H, okay, this is what we are going to use, and it is going to be multiplied by one factor here. You can look to this as if that we are multiplying summation of the Euler loads by delta H. So if we have like Euler capacities for all columns multiplied by delta H in one side, and in the other side it is summation of H times L, lateral loads times the story height, which means that the overturning moment, for example, okay, as if that we are having the overturning moment. It seems as if that we have capacities, if we assume it like this, capacities times this delta H, like they are making counterbalancing, for example, against this overturning moment. And the ratio is going to be based on Rm. So Rm should be within the range of 1 or 0.8, as we are going to find now. So this Rm, it is for braced frames, okay, Although B2 is not used for braced frames, it is going to be 1 always, but whenever that we are going to be in an unbraced case, it is going to be 0.85 for unbraced frames and mixed systems, okay, which is maybe mixed system that some base or some part is braced, other is not braced, and so on. So we are going to have Rm to be 0.8. Okay. Delta H, as I said to you, it is the drift or side sway displacement of the story under consideration. Summation of H, it is sum of all horizontal forces causing this horizontal deflection or horizontal displacement. Okay, so we need to consider here what we call it the superposition concept. Superposition concept whenever we are dealing with the case of lateral load is existing. Commonly, whenever that we have frames and we have gravity loads being applied and horizontal loads, we are superimposing two different systems together in order to make it easy for us for computational procedure or computational effort. Okay, to simplify it. So we are going to assume that this system is going to be the superposition of two different systems. One is having only gravity loads, and these gravity loads, they should be symmetric, and the system should be symmetric as well, so that there is no lateral displacement at all at the ends of the columns or the beam columns. And under these gravity loads, we are expecting small delta to take place, which is the local buckling. Plus another system which is the same system without gravity loading, but we are going to put only the horizontal loading, and it would make the large delta or the uppercase delta, which is global buckling. Okay, this type of moment that is going to be induced due to gravity loading, we are going to call it MNT, which is no translational moment due to no translational case. B1 is used to account for local BP delta here. And the case where that delta is going to be used, we're going to use MLT, which is, it is the lateral translational moment that is going to be developed in these columns. Okay, it is going to be called MLT. Here we are going to use B2, which is going to take into consideration the global B delta, the global P delta. Okay. Okay, so this is what we are looking to the problem in general. Whenever that we have a coupled gravity and lateral load, it is going to be composed of or going to be decomposed into two different systems. Okay. Well, if we are going to have unbraced condition, this is the case of the unbraced condition. As you can see, it can move here. So the system can move, right? So in this case, we are in the unbraced condition. So we have MNT and an MLT because we have like lateral side sways permitted. But the case where that we are not having, okay, we are not having, or the side sway is prevented, as in this figure, for example, the unbraced frame supports only a vertical load. The unbraced frame, as you can see here, this is unbraced frame, it supports only vertical load, as you can see here. Because of the unsymmetrical placement, as you can see, it is unsymmetric placement. It is not in the middle. It is shifted unsymmetric. So we are going to say that this system, even that it doesn't have any lateral loads, but it equals to two subsystems. The first one is going to be the gravity load only applied with restraining the horizontal displacement or the horizontal degree freedom here with what we call it artificial joint restraint, AJR, artificial joint restraint, as I put it here. Okay. Then the delta that is going to take place here, it is small p delta. This is MNT in this case. Okay. And plus another system where that we are going to remove these gravity loads and we are going to remove this support. Okay. Remove this support, and instead of this support reaction, which is the support reaction of the artificial joint restraint, we are going to put it in the opposite sense as action, as load at this point, and then we are going to expect delta here. So this is the decomposition of the system where that we are having unsymmetrical loading. Okay, so remember that if we have unsymmetrical loading on a system, symmetric loading or unsymmetric loading on a symmetric system, this would bring us to this condition, which is as if that we are having lateral translation. But generally speaking, the effect of the effect of this M lateral translation is small. It is negligible actually. And in this case, we can say P delta, which is the global P delta, will be very small, and MLT can usually be neglected. So P delta can be neglected in this case. So in this case, we can neglect P delta. We can neglect P delta. Okay. So this is the case for us here. Okay. And this is the system that we are having, which is related to the original frame for the amplification of moment. We are having the we are having M ultimate here equal to P1 plus MNT plus P2 MLT. This is the general equation that we have mentioned before in the previous video, and we have said before that it is going to be if we have like gravity loads, as you can see, and we have lateral loads, then the system in general is going to be decomposed into two systems. One system which is NT, no translational frame, and the other one is lateral translational frame. But in this system we are going to put some restraint here, and we are going to have reactions. And the other one we are going to have three reactions which are going to be applied on this the same points, but in the opposite direction. Okay. Okay. Now let's have an example in order to see how we can apply what we have explained up till now. Okay. So we have an example here, which is a wide flange. As you can see, it is a wide flange W12 by 65 steel with grade 50. It is a 995. The length is 15 feet. Is to be investigated for use as a column in an unbraced condition. So we are having unbraced condition here. Unbraced condition means that the two ends are going to move one to one another. Okay. So the word unbraced condition here, or unbraced frame, it is meaningful for us. This means large or global P delta effect with P2 with B2 is important if there is lateral load here. We are going to consider this. The axial load and end moments obtained from first order analysis. So whatever that you can see here, this is PD and PL, axial dead load, axial live load, and MD and M live load. If you look to them, you are going to find that they are coming from first order. What is the meaning of the first order here? It means that no amplification for moment has been done. This means that it's not from the second order. Second order effect is going to be taken into consideration by us. We are going to use the amplification of moment. Of gravity load, dead load, and live load are shown in this figure. The frame is symmetrical. This means that the word symmetrical here, it has a meaning. No sway due to unsymmetric gravity load or geometry. Means that we are not, if you remember, I was talking about the unsymmetrical loading, and we are going to have something at the end due to this unsymmetrical loading. Here we are not going to use it. It is symmetric. And the gravity loads are symmetrically placed. So all the loads are symmetrically placed. So we do not have any amplification coming from the side sway due to the unsymmetrical geometry or the unsymmetrical loading on the system. And also we have wind loads. This means that we have lateral loading system. So lateral loads that is going to be applied. We have wind load here. And this wind load, it makes some moment at the bottom and the top of the column. This is the wind here. We have the top and bottom values for it. Top and bottom values for it. Okay. Also, it comes from first order analysis. So the word first order analysis here means that there no augmentation of the moment. We need to make the amplification. All bending moments are about the strong axis. This means that we should not take into consideration the other axes in the interaction equation, right? In the interaction equation, we have two terms. One term related to mx and another one related to my. So we are going to talk about mx because this is the strong axis. Okay, so my is going to be 0. Okay. And then effective length factors are kx equal 1.2 for the sway case and kx equal 1 for non-sway case. Yes, this is an important issue. Sometimes this kx that we are going to have, the effective length is here, it is given different. Okay, for side sway, for the sway case, kx is going to be 1.2, and for non-sway it is going to be 1. So if the column is going to move, then in this case kx, the effective length factor, is going to be 1.2. If not, then it is going to be taken 1. This is given based on the condition of the example itself. We have no control over it. And then here we said that this is f or ky, it equals to 1. So determine whether this member is in compliance with AISC specification or not. So we are going to use what we have learned before in order to solve this example. Okay, let's go. The first step always is to find the load combinations that should be investigated first. Remember well that we have dead load, live load, and wind load. If we go back, we're going to find that we have dead load, whether axial and moment, and we have wind load. So we have gravity and we have wind. So we have lateral load. All the load combinations need to be investigated here. This is the load combination in ASC E7, which is minimum load. It is starting from 1.4 dead, 1.2 dead plus 1.6. So we need to investigate all of these load combinations. Seemingly, if you investigate these 6 load combinations, you're going to find, after looking deeper and investigation, you're going to find that these 6 load combinations are going to boil down to 2 main load combinations that need to be investigated. Means that 1.2 dead plus 1.6 live. As you can see here, 1.4 dead is not going to be dominant or governing case as long as we have like 1.2 dead plus 1.6 live, and as long as the dead load is less than 8 times the live load, so combination 1 can be ruled out. Always this can be ruled out, okay, if we have the dead load is less than 8 times the live load. The remaining equations here you can investigate. So we're going to find that some equations, they are going to be ruled out. These equations, they are going to be ruled out. You're going to find, and this one also. So we're going to find that this and this, they are the most significant, and you need to check them. Okay, so this means we have 2 load combinations need to be investigated. The first one is gravity loading only. The second one is gravity loading plus lateral loading. So here we are not expecting any lateral translation because our loading is symmetric and the geometry of the system is symmetric. So we are going to find no amplification needed for global buckling. However, here we are having already some load. Sorry, the load that is gravity load, it is 0.5 L and 1.2 dead, and this is the one that is related to the translational. Okay, now let's go and see which interaction equation that we need to use, and let's see how we can calculate the axial compressive strength for obtaining the governing equation. Okay, so remember that we need to find what is the governing equation for us, and then we are going to go through it. Okay, first of all, we need to show the composition of the loads for each load combination. So that's an important issue that we need to have. So here, this is load combination, gravity load, which is load combination number 2, and this is the load combination number 4, which is gravity loading and wind loading. So we need to have this kind of understanding. This is the gravity case. The gravity case only for load combination number 2, it is only gravity. For load combination number 4, it is gravity plus lateral load. And here we decompose them because we need to find each one and use the values of the moments and axial loads and the moments for the wind loads separately, as you are going to see. So we're going to use here, there is M NT and there is M LT. Okay, we're going to have two cases here. Okay, so now let's go back again. First of all, we need to determine the critical axis for axial compressive strength, right? This is important. Axial compressive strength is always in the equation, the interaction equation. You can visit the previous video to see this. We need to know what is the interaction equation that we are going to use. It is given for us. This is KYL equal to 15. This is supposedly to be Y. Okay, and this is for X. KYL equal to 15. And for X, okay, because we are going to use the tables directly. So KXL over RX over RY, which is 1.75. This is coming from the table. As we said, we cannot enter the table unless that we modify the KY that is already, because the horizontal or the vertical most left column, it is related to the radius of gyration RY. So we need to enter the table with modifying this by multiplying RX over RY in the denominator. And you can recall this from the videos related to the column tables. So we have KY times L equals to 15. However, that for KX times L, it equals to 1.2 times 15. Okay, because we have KX is 1.2. This would equal to 10.29 foot, which is less than 15. This means that KL is the critical for Y. Y-axis is the critical one for us. No need to consider the KXL or the effective length in X. KY, the common one, is going to be the dominant, or we can say the governing case. Okay, from the column load table with KL equal to 15, we can obtain the column strength directly. Please pause the video here, go to the specification and find whether that's 662 or not for our cross section. This is the table, W12 by 65, and this is for LRFD. If we're going to look here, this is for 15. We can find that 662 as we said before. So it is here, 662, it is right. Then we are going to make two cases here, where the first case is for gravity load combination only, no side sway. This is for load condition number 2, right? And then we have another case. Which is for gravity plus lateral, which is for load condition number 4. Gravity loads, which is dead load and live load, and here we are having wind load. So we're going to repeat what we are going to do 2 times. For the gravity loading, it is very easy for us now. For gravity loading, it is no side sway. So first of all, we want to check what is the Cm. The Cm is taking into consideration the distribution of moment for beam column. This is the equation given. We need to take care of M1 and M2, the sense of them, and the ratio. M1, it is the small moment. M2, it is the larger moment. And the sense of them, if both of them are counterclockwise or they are opposite. And this is 90 and 104. Let's go back and see here. It is 90 here and 104. This is, as you can see, it is counterclockwise. This one is counterclockwise. This means that we are going to have positive sense. We are going to have a positive sense for this case. Okay. This is the ratio, and this is Cm. Cm is 0.256. What is the meaning of this? This means that we are going to multiply B1 by this value. This means that we are going to reduce the B1, which is the amplification factor, by almost 75%. This is what Cm equation is telling us here now. Okay. And now let's go for the calculation of B1. We want to calculate B1 now, the amplification factor, right? If you remember, we said that it equals Cm here, 1 minus, there is alpha PR here over PE1. From where this equation? Please visit the previous video. Then we are going to have PE1 equals to pi squared EI over K1L. Everything is known for us. Take care of EI and IX, which is IX for the cross-section strong axis. KX, it is 1 here. Do you remember? We said that for the unbraced condition, it is 1. And L, it is 15 by 12, which is the conversion between foot and inch. This gives us 4,708 kips. Okay, so this case involves no side sway. So Kx for the braced condition is used because already it has been given for us. Do you remember? Yes, Kx, this is for sway, and Kx for non-sway condition. Okay. The amplification factor for the non-sway, still we are side sway, no side sway. Okay. In this case, B1 is going to equal, this is the equation, the famous equation that we have used last time. Everything is known now, Cm. Alpha, it is going to be 1 because we are using LRFD. PR, it is going to be the ultimate load, which is 454. 454. Okay. This is from the previous 454 if we are going to talk about our gravity loading. 454. And then if you substitute, you're going to find 0.284. This is B1. As we said, B1 should always be larger than 1 because it is an amplification factor. So if it is less than 1, then the minimum value should be exactly 1. We should use it as 1. And now we can calculate MR. MR would equal to M ultimate. It should equal to the general equation B1 times MNT plus B2 times MLT. We do not have MLT, no lateral, so it is going to be 0, right? So it is 0 here. B1 we know it, which is 1, and MNT we know it already, 104. Okay, the maximum moment here, this moment, right? Okay. Then, based on that, we can, from the beam design charts, we can obtain, we want now to get the denominator of the equation. Do you remember the denominator of the equation that we are seeking for? Yes, we want to get this part of the equation. So first we calculate this part to know which equation that we're going to use. Then we need to calculate this part. Already M ultimate X, it is the part that is including B1 or B2 if the case is sidesway. Our case here is non-braced or sorry, our case is braced, no side sway. So it is already, we have obtained M ultimate X. Now we want to get the from the charts the flexure strength. Let's go back. Okay, and get it from the charts. Okay, we have LB 15. This is the critical one. Let's go and get the, remember, this is the charts here that we are going to have, something like this. So we're going to go with 15 and then go here and check this value. After that, remember that CB equal to 1 for all charts. So we need to calculate CB, and then we're going to get value for CB. If this CB, for example, 1.6, multiplied by this value, we found that it would bring us here. This means that we cannot use this limit. We need to use this limit, the horizontal line. This horizontal line, whether it is the flexural local buckling in case of non-compact sections, or it is going to be the plastic limit in case of compact sections. It depends. So now what we are going to do is getting these values for CB equal to 1, all charts for CB equal to 1. So we have MN and MP, the nominal strength and the plastic strength. Let's obtain them. Stop the video and go to the manual and check these values now. Okay, so these values, as you can see here, you can go to the wide flange shapes for W15 by 65 here, and then go with 15, for example, and then you're going to find this is what you're going to find here. Here, this is the value, which is 340 almost. And the horizontal line, if you go to the horizontal line here, this is the horizontal line, 12 by 65. It gives you 356 foot kips. So this is right. I mean that what we have obtained here, right, 340 and 356. Okay, the section seems to be, as I said here, this is the limit, nominal strengths. This one is the plastic limit, as we have mentioned before. Okay, that's very fine now. And we can go directly to the next part, which is related to the calculation of CB, the real CB for us. CB for our case, for the unbraced condition, we have 90.0 at the top, 104 at the bottom. We can draw a line and then get the values of the moment at A, B, C. And we have this is M maximum. Why we need M maximum and A and B and C moments here? Because we are going to substitute in this equation of CB. If you do not know what is the CB, please revisit what I have explained 2 or 3 videos before. CB is going to take into consideration the effect of moment gradient on the strength of flexural members. It is for beams, basically. We are using here for beam column because beam is considered to be one part of the beam column that we need to take into consideration. The behavior or flexural behavior is going to be considered in beam column as it is in the beams. So we substituted simply in this equation with all the moments known for us from the unbraced condition, gravity. Remember, we are talking about gravity condition, load condition number 2. Load condition number 2. If you calculate, you're going to find that CB equal to 2.24, which is very high, very big. This means that this equation or this moment here, 340, this limit that we have obtained, it will be multiplied by 2.24, and it will be something here, of course. So it will exceed the yielding limit, the plastic limit. Then our limit is going to be 356 in this case, right? So when you multiply 2.24 by 340, it will exceed the plastic limit. Then we're going to use the plastic limit. The plastic limit is going to be our flexural plastic limit or flexural strength of the beam column under consideration. Okay? Okay. Now let's go to the next. Now determine the appropriate interaction equation. We know everything now. We know P ultimate over phi C times Pn. Already we got this before from the combination. And this 1662, already we have obtained it. This is for the column, from the column load tables. Found this value is 0.6 something, larger than 0.2. Do you remember? Do you remember what we have said? So this means that the axial load is dominant. This means that we are going to reduce slightly the moment term and keep the axial term as it is. There is no reduction here. If it's less than 0.2, then the opposite will happen. Here we are going to multiply by half, and here we are going to remove this 8/9. But anyway, this is our case now. And as we know that we do not have any lateral or the opposite or the perpendicular moment, ultimate y is 0. So this is 0. This term is going to be 0, right? Everything is known for us. The axial term gives us 0.6 as here. M ultimate x already we have obtained it after augmentation using B1. Fortunately our B1 was 1, so it is no augmentation here. The flexure strength coming from the beam charts, we found it easily because CB takes us higher than the plastic limit, so we put the plastic limit here. Simply you can obtain the value for this case. It is 0.94, less than 1. It is okay. So this is for what? Remember, load case number 2, which is gravity. Again, gravity load. Gravity load. We do not have anything related to the lateral translation. Now let's go to the second case, which is related to gravity plus lateral load. So we are going to expect we have P delta and we are going to have P delta. Local and global B delta. We are expecting to have B1 and we are expecting to have B2. Okay, two things. Okay, now let's go and see. The first step is to put what we know and put it in front of us, right? So first of all, we have two cases here. The case of the gravity, 1.2 dead plus 0.5 life, and the case of the wind, 1.6 wind. Both of them, they are composing load combination number 4, right? But we separate between them because this part, it is the LT part, lateral translational part. This part is coming from no translational part, right? This is gravity only, dead load and live load. And our system is, as we said, symmetric in terms of loading, symmetric in terms of geometry. Okay, so here this part is like no translation, this part is lateral translation. Okay, P ultimate here is 212, right? MNT, no translational, the maximum one. We're going to take the maximum. We have 40.5 and we have 47 point something, so 47.6 here. M lateral translational, it should be the maximum if we have different values, or one of them if they are the same. It is 212. So everything is given for us. For the brazed condition, Cm is going to be 0.6 minus 0.4 M1 over M2. Okay, our case here, it is for what? The brazed condition. We're talking about the brazed condition. No translational here. So look here. We're having what? 40.5, the smaller moment, which is M1, and 47.6, the larger moment. They are in the same sense. They are in the same sense. This means that we have, in the same sense, means that it is going to be positive here, right? The ratio is going to be positive. Then we substitute in this equation, and we are going to find Cm equal to 0.2597. What is the meaning? What is the significance of this Cm value? It means that B1, the amplification factor for the case of no translational case, which is the dead load and live load, would be reduced by 75%. Can you imagine this? This is the contribution of Cm. Then we are going to calculate B1 now, but if we want to calculate B1, we want to know Cm and we want to know PR, which is already given for us in our case, which is the P ultimate. Alpha, it is 1 for LRFD and 1.6 for ASD, and we want to calculate PE1, Euler load, right, for this column. So Euler load is going to be 4,708. From where we got it? From the previous case, because PE1 won't change. It will not be changed. It will be the same. It will be the same. Okay, so you can get it from as we have explained and obtained it in the previous slides. Substitute in this equation and you're going to find that B1 equal to 0.27 something. As we said, B1 should not be less than 1. Then we are going to use B1 equal to 1 in this case. What is the meaning of this? What is the meaning of V1 equal to 1? This means that no amplification for moment due to no translation condition. Means that the dead load and live load, axial forces and moment, they are not going to be amplified. The PE delta, small p delta that is going to take place here is not going to be important. It is negligible. Okay, so the gravity loading are okay for us. Now let's go to the other part, which is the lateral translation part, right? The wind contribution, okay, which is going to compute, we are going to compute B2 for wind, right? So to compute B2, the amplification factor for side sway moments, the elastic critical buckling BE2 must be calculated. We need to know BE2. Remember, it is summation, means that it is for the entire story. We have many columns, so we should calculate it for the columns in the story, not only for one column. As I said many times, there is a difference between B1 and B2. B1 local, B2 global. We are talking about summation here. There is summation, right? This summation means that we need to know all the columns condition, but we do not know, and the example didn't give us any information or didn't provide us with any data regarding the capacities or PE2 for the columns. Okay, so there are not enough data available for either ASIC equation, the two equations C2-6a and 6b, but if we assume the ratio of the applied axial load to Euler load capacity is the same for all columns in the story as for the column under consideration, so we're going to consider simply that the column under consideration is going to be, all other columns are going to be similar to it. That's it. It's a very simple, straightforward assumption, but it is not accurate, of course. If we have more information about other columns, then we need to use them. Then this would make our life easier when we are going to calculate B2, right? Because here our PNT equals to P ultimate, okay? So the summation here, the word of the summation means that we have like 10 columns over the summation of the PE2 for 10 columns. So we said that the ratio of all the 10 columns in the numerator, it is the same as the denominator. I mean that the ratio of this column that we are talking about. So the summation, I mean that the summation is going to be cancelled. We're going to use only one column as representative, okay? So PNT in this case, it is going to be P ultimate only. And PE for all columns is going to be PE2 for this specific column, okay? So in this case, we are going to obtain PE2. It equals to pi squared EI over K2L to the power 2. Again, K2 here, it is 1.2. Why? Because we are talking about the unbrazed case is used. It is given for us in the beginning of the example. 1.2 should be used for the unbrazed case. Do you remember this? Yes, 1.2 for sway case, which is unbrazed case, right? Okay, so now we have everything here. We know E and I, K1.2, L, it is 15 by 12 for unit conversion. Then we got this PE2, which is going to be here. Easily we can obtain B2 now, right? So B2 is going to be 1 over alpha. It is 1 because we are talking about LRFD. If it's ASD, it is going to be 1.6. Okay, why for this? Because the derivation of this B2 was based on load factor design, not based on ASD. Okay, and then PNT already 212. Already this is given for our case, right? The PNT for coming from, this is the axial loading, right? PNT 212. From where? Let's go back and see. Okay, which is, sorry, no, not this one. I'm sorry. This is the moment. Okay, this is the moment, because this is the wind. We are talking about the vertical axial load coming from NT, which is this one, 212. Okay, this is PNT. Okay, this is the moment. This is something else. Okay, so we are still in the load combination for. When we are talking about B node translational, we should obtain it from the gravity load. We should obtain it from the gravity loading. Okay. Okay, now we have everything here, and PE2 already we have obtained it, and it gives us 1.069. What is the meaning of this again? Do not leave the basic principles obscure. You need to visit this or to remember or recall these principles from time to time. B2 equal to 1.069. First of all, it should be larger than 1. It is larger than 1 by 6.9%. This means that the global buckling or P delta effect would increase the moment or amplify the moment, okay, in the side sway by 6.9%. Okay, we need to consider this in our calculation. So the total amplified moment in this case, we are going to have MR equal to M ultimate. B1, which is 1, already we have done this before. So MNT is not going to be changed. MNT is not going to be changed. It would be maintained as it is, 47.6, right? The issue is in B2, it is going to be exactly 1.069. Then multiplied by MLT, which is 211.2. This is coming from the wind. Do you remember the wind? We have the wind case 200.2. Moment. We're talking about moment. B1 and B2 are used or amplifiers for moments mainly. Okay. Even that for axial load, we said that B2 is going to be used, but it is negligible as we mentioned before. So although the moments MNT and MLT are different, they are distributed similarly, and CB will be roughly the same. Yes, that's right, because CB actually should be calculated for each case. Okay, but again, it will the difference will be small. If you want to go through it, you can do it, and you are going to find that CB is not going. If CB, for example, here CB was 2.24. If you calculated for MNT, for example, and you found that it equals to 2.1, for example, so it is okay, because at the end here, the limit, you are obtaining the value here. This means that you are going to multiply it at least double, at least 2. So it is going to be here 2.4 or 2.1. It is going to be the same, larger than the plastic. No, the limit for us is going to be the plastic limit, MP. Okay, so this small difference, it won't make any big deal. Okay, at any rate, they are large enough. Yes, more than the plastic limit. Okay, this, after that, we are going to use which equation that we need to use. In this case, it is P ultimate over phi C Pn. When we calculate it from the inputs that we have calculated before, it is 0.32, larger than 0.2. This means that we are going to the case where that the axial force is dominant, so no reduction for the axial force, but there is slight reduction for moment. This means that when we use all the input here, remember that we don't have anything on the biaxial moment or another my moment. We have only M ultimate, the augmented one, okay, the augmented one, this one, after using B1 and B2 and this stuff. And here phi B MNX, that is already 356 from the charts of the beam charts. Then we found that all of this equal to 1, which is okay. It is exactly the same. It should not exceed 1. This member satisfies the AISC specification requirements. Okay, I think that this is the end of this this video. I hope that you have understood what really B2 is all about, and the basic principles behind using B2, and the amplification of moments in case of not braced frames or sidesway permitted frames. Thank you for listening, and see you in the next video.